Hi everyone, my name is Evan Juras and I'm a computer vision engineer at my own consulting firm, EJ Technology Consultants. I have a background in hardware engineering, but I've recently, over the past few years, gotten to work on several fun and interesting computer vision projects, and I've learned a lot in the field of computer vision. I love helping people solve computer vision problems, and I love teaching people about different topics related to computer vision. So I'm happy to be here today to talk to you about practical image data augmentation methods for training deep learning object detection models. Let's get started. My goals for this presentation are to introduce practical image data augmentation methods that you can use to increase the size of your dataset. Now, by practical, I mean effective and low effort. Effective means that you will be able to use these methods to see concrete improvement in the performance of your object detection models, and low effort means that you will only need to spend a minimal amount of time implementing them. I'm hoping you'll be able to walk away from this presentation with some examples, some ideas, and some tools to improve your own detection model's robustness and accuracy. I'll also discuss some considerations that you have to think about when applying data augmentation. So what is data augmentation? Well, it's just creating new images for your training data set by modifying existing ones. So for example, I've got a picture of a blue grosbeak here, and I've augmented it into 4 different images. And the examples I've got for augmentation methods are pixel clustering, embossing, perspective transform, and flipping, cropping, and blurring. Now, why do we want to use data augmentation? Well, there's a few good reasons. The first one is that you can use it to increase the size and variety of your data set. This will help to prevent overfitting for your model. It will increase the robustness of the features that your model is learning to detect, and it increases the variety of visual environments that your model will work in. Now, these all kind of go hand in hand. If you only have a few images for your training data set, your model will be very good at recognizing objects in those images, but when you start to show it images from other conditions or from other situations, it won't work as well. And that means it will generalize poorly. If you increase the variety of images by using data augmentation, then it can work in different lighting conditions or from different perspectives or different camera resolutions and things like that. So generally, it can help it to have better generalization and detect objects in more situations. A second reason to use it is if you need to resolve class imbalances in your data set. So a class imbalance is basically if, say you're training a 3-class model and you have a ton of images for your first class, but then not very many images for your second and third classes. If you train a model with that data set, it's going to become biased towards that class with all of the images. So for an example here to the right, I've trained a bird, squirrel, and raccoon model. And on the top there, you can see that it's very biased towards raccoons. It wants to identify everything as a raccoon. And it kind of reminds me of my friend's son who just turned 3 and just is in love with raccoons. So every time he sees an animal like a deer or a cat or anything, he'll say, "A raccoon, I love raccoons, raccoon." And so he incorrectly identifies everything as a raccoon. And that's the same thing that this model is doing. It's biased towards raccoons. If you resolve the imbalance in that data set and retrain the model, then you can help reduce the bias of that model, as shown on the bottom there, where it does correctly identify a raccoon, a squirrel, and a bird. A third reason to do this, to do data augmentation, is to save time over manually acquiring and labeling images. Any of you that have had to train your own object detection model know that it's pretty painful to go through a data set and label thousands and thousands of objects in images. It takes a long time and it isn't very fun. So say you wanted to create 50,000 images for your data set. Well, if it takes 10 seconds to label each image and you have 50,000 images, that's 139 hours of time just spent labeling. It's not very fun. Whoever you give this task to of labeling all those pictures, they're probably going to quit their job after the first day. So we don't want to do that. We want to make it as automated as possible. There's several different methods for doing data augmentation. There's 3 categories I'll talk about here. One is basic image manipulation. This is doing things like geometric transformations where, for example, I can rotate an image of a squirrel. I can also do things like translate it or crop it. or do a perspective transform. Those are all geometric transformations. There's also color space transformations like this hue saturation value shift that basically recolors an image. And then kernel filters. The example I have here is a dropout filter that will go through and randomly drop out batches of pixels from the image. Other examples of kernel filters are like a Gaussian blur or pixel clustering filters. A second category of data augmentation is using neural networks to do data augmentation. So you can have a neural network to create images to train another neural network from. The top example here is a generative adversarial network that is pretty good at generating images of dogs and cheeseburgers. So you can generate a bunch of images of dogs and cheeseburgers and then use that to train your dog and cheeseburger detection model. And maybe you can set up a program that alerts you when the dog gets too close to the cheeseburger, and so the dog doesn't eat it, or something like that. Another option is neural style transfer. This is when you take an image and feed it through a neural network that will apply and transform the image to match a different style of image. So it's just another way of creating new images from an original image. In this case, I've turned a regular tiger into a white tiger. A third category that I like is synthetic image generation. This example I have here is from Synapse Product Development. It's a company that I used to work for in Seattle. And what they did is basically they want to be able to detect these kind of Lego-like circuit building pieces. And they created photorealistic models of these pieces in Unity, and then they created a script to programmatically rotate the objects around and impose them on random backgrounds, and then they train the object detection model using these images. And it actually works very well. I have a link to a blog post that talks more about this method if you're interested in it. I think you'll be getting a PDF of these slides after the presentation, so you can follow that link if you're interested in learning more about it. For this presentation, I'll mostly be talking about the basic image manipulation methods. I'll be giving some examples and tool sets for how to do it, and then also showing how effective the different types of transformations can be. Before I get into that, I want to make a quick note about data augmentation as it's applied to object detection. Augmenting object detection datasets is more challenging than when doing image classification or augmenting images for image classification models. This is because with object detection, you're not just transforming an image, but you also have to transform the object key points or bounding box coordinates. So for example, I've got an image of a bird here with key points that define where the bird is located in the image and then a bounding box around the bird. So if I rotate this image, I also have to apply that same transformation to the XY coordinates that show where the key points or the bounding box is. And that's a little bit more difficult than just simply rotating the image and labeling it as a bird. You also need to make sure that augmentation doesn't destroy your label information. With object detection data sets, sometimes the object can occupy a small portion of the image, and there's a risk of cropping out that object and basically destroying the label. And then you've created an image that doesn't have any useful information for training the network. I've got an example for that with a 9 of spades. If you're trying to train a playing card detector and then you accidentally crop out the 9 of spades symbols, then it might be harder for this, or basically that image isn't useful for training the network anymore. At the end of the presentation, I'll talk more about some different considerations that you have to think about when doing augmentation for object detection models. There's a large variety of tool sets available for doing data augmentation. I'll go over a few of them and talk about the pros and cons for each of them. The first option I'll go over are these open source GitHub libraries that are available. Some examples are Imgog, Augmentator, and Albumtations. The pros of these are that they're free, they tend to be well documented, and they have good examples to teach you how to use them. Some drawbacks are they may just become unavailable. The person that put them on GitHub may decide to delete them, or more likely they'll just get too busy and stop maintaining those libraries, which is something that I'm guilty of myself. A second option is using OpenCV, which is a very common computer vision open source library that has a lot of image manipulation functions that you can use to manually create your own augmentations. Pros of this are it's free and you can have very tight and flexible control over the augmentations that you're doing. For example, you can write something that says like, I'm going to go to every 5th pixel and turn it some shade of gray, something like that. The drawback is that it takes more time because you have to write all of these augmentation functions yourself. TensorFlow, which is Google's open source framework for machine learning, the object detection API provides augmentation options that can automatically be used during pre-processing. So when it's preparing a batch of images for training, it will go to your data set, grab some of the images, and then randomly apply these augmentations to them before feeding it into the training algorithm. The pros of this are, again, it's free and it's very easy to use. Basically zero effort. You just have to open a configuration file, add a couple lines to it that say, I want to crop these images, I want to randomly flip these images, and things like that. And then it'll automatically do it for you. The cons are there's not that many operations available compared to those open source GitHub libraries, which have hundreds of augmentation options available. Object detection API doesn't have very many. And since it happens automatically, if you're not aware that it's happening, you can accidentally double augment your data. Basically, you can have augmented images in your original data set and then be automatically applying additional augmentations to them. So you'll have double augmentations, which can get kind of confusing for the model. As a side note, the TensorFlow Keras library has an object data augmentation features to it, but those are only for image classification models and not for object detection models. But hopefully they'll add object detection functionality in the future. So my favorite of these options is Imgog. Again, it's well documented and it has good examples and it's just easy to use. So I'll give a quick example using Imgog to apply augmentation to a single image and just show you how easy that is. I've got some code that I'll show here, but I'm not going to labor over the code. I just want to show how few lines of Python it takes to do this. So the basic process is that you define an augmentation sequence, which here I've got a sequence that says, okay, I want to horizontally flip 50% of the images. I want to crop every image randomly between 0 to 10%. I want to blur them, recolor them, rotate them, and translate them. And there's hundreds of different options that you can use here in defining this sequence. And then once you've got it defined, you can load an image. So I'm going to load an image of a squirrel from a folder that contains a bunch of images of squirrels, and then apply the augmentation to that image. And it's as simple as just one line where you feed that image into the augmentation sequence and it spits out an augmented image. And then you just save that augmented image to a different location, and there you go. And you can write this code to loop as many times as you want. You can loop through every image in a folder, and then for every image, create 5 augmented random images and things like that. So I ran that example on a single image of a squirrel, and I ran through it 10 times, and these are the results. Basically, you can see the different amounts of transformation or recoloring or cropping that occur with these augmentations. Now, these augmentations are a little bit excessive, but I'm mostly just showing as an example the kind of transformations that you can do. On the resources slide at the end of this presentation, I have a link to a GitHub repository I created that has some code examples that show how to do this augmentation, including with key point augmentation for object detection. So if you're interested, you can go and check those out. Now, there's hundreds of different types of basic augmentations that you can do on an image, and you might be wondering, well, which ones should I do? Which ones are the most effective? I found this paper where 2 people experimented on the Caltech 101 dataset and basically applied a bunch of different augmentations to the dataset and then trained a new model using those augmented datasets. The augmentations they tried were flipping, rotating, cropping, and etc. 6 different augmentations in all. And they compared the baseline accuracy to the accuracy of the models they trained with their augmented datasets. And these are the results they got. They found that cropping was definitely the most effective augmentation method, but that every augmentation method improved accuracy at least a little bit, with flipping and rotating providing about 2% improvement. Now, the augmentation you want to use depends on the data set and the conditions that you want to apply your model for. So saying you're making a person detector and you have a bunch of images of people facing this way and maybe some images of people facing on, but then you don't have any images of people facing this way. And so your model, if you train it with that data set, is going to be good at detecting people face on in this direction, but it might not be very good at detecting people that are facing to the left. So to resolve that, you can use data augmentation to flip all of those images of right-facing people to make images of left-facing people. And by doing that, hopefully your model will be better at detecting both right, left, and frontward-facing people. So that's just kind of an example of how you can think of which augmentation method you might want to use to improve your data set for the conditions that you're expecting to use your model in. So this experiment inspired me to do my own experiment to just demonstrate simply how augmentation can improve performance of a detection model. A side project that I've been working on is a smart bird feeder. Any of you who have owned a bird feeder know that it's not just birds that like birdseed. Squirrels and raccoons also really like birdseed, and they'll go and they'll empty out your entire bird feeder while the birds just have to sit in the tree and starve. So to prevent that, we could do something like set a camera up right next to the bird feeder, and that camera maybe will take pictures of birds when they come by or count how many birds are at the bird feeder. But when it detects a squirrel or a raccoon, it'll do something like sound an air horn to scare the crap out of them. And it'll probably scare the crap out of you too in the process, but we won't worry about that right now. So one thing I realized when I set out working on this bird, squirrel, and raccoon detection model is that it's pretty hard to capture a live squirrel and get him to sit still for you in front of the camera so you can, take images and test out your object detection model. So instead of capturing a live squirrel, I just decided to use some bird, squirrel, and raccoon stuffed animals since they'll be a little bit easier to work with, and just for the sake of example. I started with an unbalanced data set. I took 5 pictures of the bird, 30 pictures of the squirrel, and 30 pictures of the raccoon. And then I used augmentation to create 25 more bird images. I just applied cropping and flipping to the 5 images that I had to create 30 images total. And now I have a balanced data set of 30 images of each class. I then trained 2 different models, one model using the original unbalanced data set and a second model using the augmented data set, and compared their performance. And as a result, I found that the augmented model was better at detecting birds. So I took the models and I applied them to a test set that contained equal amounts of birds, squirrels, and raccoons, and ran a MAP calculation to determine their accuracy. The base model didn't do as well at detecting birds in each of those images, so it got a lower mean average precision score, while the augmented model was better at detecting birds in those images, so it had a higher score, a 12% improvement almost. MAP score is great. It's a great metric for comparing models, but it's kind of hard to translate that into, well, how well is my model actually performing? So I also took a video of the bird, squirrel, and raccoon stuffed animals and ran detection using the base model and the augmented model on the same video. And I'll show you how that works. I wrote a script to tell me how many times the model correctly detected of bird, squirrel, and raccoon in each frame, and count how many frames that it correctly detects them. So if you squint a little bit and watch both videos, you can see that the one on the bottom, which is the augmented model, does do a little bit better at detecting the birds. It's not perfect. I still only have 30 images per class, and this is a YOLO v3 tiny model, which is a more lightweight model and a little bit less accurate. But in general, you can see that the augmented model does do better at detecting birds. It correctly detected 67 of the 250 so frames, while the base model only detected 18. So I did see a significant improvement in the accuracy of the model that used the augmented data set. So that's great. It only took me 10 or 15 minutes to create those extra 25 bird images, and I got this much improvement out of my model. Okay, so now I'm going to switch gears a little bit and talk about a special augmentation method I used that I call the random background augmentation technique. I use this method to generate 50,000 images of playing cards and use those to train a card detection model, and it works very well and it's very accurate. The way this method works is I take images of playing cards and impose them on random backgrounds, and I vary the scale, perspective, position, and rotation of the playing cards for each image. Using this method, I can generate thousands of variations from a single image, so it's pretty effective. It works well because it reduces the likelihood of false positives. So for example, if there's a black polka dot in the image, the model might think that that looks like a spade, so it might identify that as a spade. But if I include a bunch of background images that have black polka dots that aren't labeled as spades, and it sees that spades are, sees a label of a spade in that same image, that kind of helps it learn what is a spade and what isn't a spade. Like let's call a spade here. It also forces the model to build a robust feature space. It gets very good at recognizing which patterns belong to a certain class. So for instance, it knows which patterns to identify as a 7 of clubs or which patterns to identify as an ace of hearts. The method is also effective for other applications that involve 2D static objects. Some examples besides playing cards would be street signs or book covers or decals. So I'll go over the workflow that I use to generate these playing card images. I started by recording the cards in various lighting conditions. I just placed them on a background and moved a light around while I was recording them, and got 52 videos of the cards. Then I used a script to isolate the cards from these images and wind up with about 100 or 200 isolated images of each card. Then I used a bigger script to randomly select images of cards from that batch of images and impose them on a randomly selected background in an automated fashion. And then for every image that was automatically generated, it also saves the bounding box and label data in an XML file. So when everything is said and done, I have 50,000 images of playing cards and the label data to go along with them. I then used these 50,000 images to train a playing card detector using Yellow v3 on the DarkNet framework, and basically resulted in a very highly accurate playing card detector. So this is another side project that I've been working on that I call Rain Man 2.0. It's a blackjack playing card counting AI. And the idea is that you'll be able to deal cards out in front of a camera, and it will detect the cards and keep track of a running count for blackjack, so you can use it to count cards. And I'll show an example of how it works here. So as you can see, the model is very accurate at detecting the cards. It's trained off of the rank and suit symbols in the corner of the card, and it works well at identifying those even when the cards are starting to overlap each other or when there's a busy background. And it's very accurate. I can deal through a full deck of cards, and I've got my program to set up to automatically do +1, -1 counts like I was counting through a deck in blackjack. And it keeps track of which cards have come out of the deck and which cards are still remaining. And it works very accurately, and I'm happy with how it turned out. If you're interested in this project, I have a YouTube channel where I talk about it. The channel is Edge Electronics, EDJE Electronics. If you search for Rain Man 2.0, this video should be the first one to pop up, and you can learn more about it and what my plans are for it and where it's at so far. So we're getting closer to the end of the presentation now, and I wanted to go over some different considerations that you might need to think of when approaching data augmentation. One of the question is when should you perform data augmentation? Should you augment all your images before training, or should you augment your images during training? Well, both are good methods, but there's just a couple trade-offs. So if you have a batch of images and you augment them all before training, that will reduce the training pipeline overhead, which will ultimately speed up training, but it can take considerable storage space. So say you wanted to go crazy and make 1 million augmented images. Well, if you have 1 megabyte per image and 1 million images, that's a whole terabyte of hard drive space. So you better have a big hard drive. Just something to keep in mind. You can also augment images automatically during training. Basically, you can set up your preprocessor to go grab images from your original data set and randomly apply augmentations to them and then pass them into the training algorithm. One drawback of this is that it requires more processing power, so it'll ultimately slow down your training, but it does reduce and simplify the storage requirements. Another benefit of doing this way is It increases the statistical variation that you'll be creating with augmented images. Since basically it's going through and randomly selecting images and augmenting them, it almost has like an infinite space of variations that it can create. Whereas if you augment all your images before training, you still have added a lot of statistical variation, but you have a fixed amount of variation in your big augmented data set. Whereas if you're doing it on the fly, it has an infinite kind of space to generate variation from. So this results in a better improvement in generalization. Both of these methods, of course, will improve the generalization, but if you do it during training on the fly, you might see better improvement in generalization. Another question is, which data set should you augment? So of the 3 data sets, you have a trained data set, a validation data set, and a test data set. For the training data set, yes, you do want to augment the images in your training data set. That will allow your network to learn the different variety of visual conditions that your object will be in. It'll allow it to learn robust features to detect the objects. So yes, you do want to augment your training data set. The validation data set is used usually to monitor the progress of training, and you can use it to tweak things, hyperparameters during training, like learning rate or momentum. But most of the time, most of the applications that I've seen and I've done are we just take an existing model and we do transfer learning to teach it how to recognize new classes. And if you're just doing transfer learning, it's not as critical to tweak hyperparameters during training. So you don't necessarily need to augment your validation training data set. And finally, there's the test data set. This is the data set that once you're done training your model, you go and you apply it to the test data set and see how well it actually works at detecting the objects. And you should not augment the images in the test data set because the test images should all represent real world conditions. And if you have augmented images in there, that's a synthetic condition. It's not a real world condition. Some other considerations you might think about. I might start getting a little hand wavy here, but these are just some of the questions that I had as I was approaching data augmentation the first time. One is like, well, how many images should I have? If I can make 50,000 images of playing cards, is it better to make 100,000 images or 200,000 images? And what I've found from research and from experimentation is generally more is better, but more images are better, but there is an upper limit to effective data set sizes. For example, my playing card model, I used 50,000 images and it works very well. When I used 100,000 images, I didn't really see any difference in improved performance. So it was kind of had hit an upper limit of effectiveness. It's also dependent on your application. So if you're training an object detection model to be used in a wide variety of visual conditions, like maybe a camera that will be both indoors and outdoors and maybe like overhead or pointing in people's faces, different resolutions of cameras or different levels of focus and blurriness, or, maybe if you want to use it at a midnight EDM rave in a warehouse and use it in a waiting room at the DMV, then, you're going to have a wide variety of conditions that you're using it in. And in that case, you'll want to use more images for your data set to make sure you're covering all the variations in visual conditions that your model will be seeing. And you can use data augmentation to help with that. Pete Warden is speaking at this conference, and he is a staff engineer at Google that helped develop TensorFlow Lite. And his rule of thumb that I found is that you basically should use about 1,000 images per class if you're training a model from scratch. Just a general rule of thumb to keep in mind. Another question is, what should the ratio of augmented to original images be? Like, can I just use one original image and create 1,000 augmented images and still have a good result? The answer is no. You still need to have enough images in your original data set to provide enough variation for the model. If you only have 50 images and you create 5,000 augmented images from those images, the model is still going to be heavily biased towards those 50 original images. I found that a ratio between 5:1 or 10:1 of augmented images to original images works well. Another thing you want to consider is the resolution of your images. The resolution should be similar to the resolution of the camera or the video or the images that you'll be using in your application for the detection model. And Keep in mind that higher resolution images require much more memory during training, so you'll either need to buy a computer with a lot of RAM or just live with slower training. So there are some limitations of data augmentations. One of them is that augmentation must be label preserving. Unsafe transformations can destroy the label data. So for this example, I have a picture of a raccoon that I've darkened, but I've darkened it so much that you can barely see the raccoon anymore. The neural network really isn't going to be able to glean any useful data from this image, so I've effectively destroyed the data in the image. Another thing to keep in mind is that augmentations must be dataset aware. Transformation can change your label. So a classic example is if you take a 6 and you rotate it 180 degrees, well, that changes it into a 9. So your label of 6 isn't correct anymore. Or a transformation can make something nonsensical, like you turn a yellow banana into a blue banana. Doesn't really make sense. One of the papers I read said that you shouldn't rotate animals upside down. Like it wouldn't make any sense to see an upside down cat in the real world. But whoever wrote that paper probably never owned a cat. And finally, you can't use data augmentation to overcome a limited data set. You can't create new classes from other classes. So I'm from Montana, and I thought I would throw a bear example in here for everybody. Quick quiz. Of these two images, which one is the black bear and which one is the grizzly bear? Hopefully you're able to identify that the black bear is the one on top and the grizzly bear is the one on bottom. The way you can tell is that grizzly bears have more rounded ears, while black bears have pointier ears, and grizzly bears also have this big hunch over their shoulders that black bears don't have. Now, this is a pretty important classification task because say you're hiking through the mountains in Montana and you are walking down the trail and all of a sudden a black bear appears 100 feet in front of you. Well, with a black bear, you can just stay calm, keep your distance. You can even just circumnavigate around him and keep going down the trail and, keep going on with your hike. But if you see a grizzly bear, you just have to turn around and get the hell out of there. So it's a pretty important task to classify these correctly. And if you're trying to make a model that can distinguish between grizzly bears and black bears, but you don't have any images of grizzly bears, well, you can't just somehow augment the black bear images to create grizzly bear images, because if you try and train your model with that, it'll just be confused between what a black bear and a grizzly bear is. And your trail hiking robot will wind up getting eaten by a grizzly bear. So we've reached the end of the presentation. I just wanted to quickly summarize the things I talked about. One, I showed you some data augmentation techniques that you can use to increase your model's accuracy with a minimal amount of effort. I discussed a random background augmentation technique that's very effective for generating images to train models that can detect static 2D objects. If you're using data augmentation, you need to consider when and where to apply augmentation and how many augmented images you want to create. And finally, data augmentation does have some limitations that you need to think of and keep in mind as you're using it. We'll do a Q&A session in a brief moment, but first I wanted to go over the resources for this presentation. I have a couple links to GitHub repositories. One contains the example code that you can use to do image augmentation for an image classification model or for an object detection model. Another is a link to the script that I used for generating all those synthetic playing card images. If you're interested in getting in touch with me, or if you have some questions about data augmentation or need help with data augmentation, you can check out my website or email me directly. And then these are some of the references that I used for researching this presentation, and they have some pretty good information about data augmentation and more details about how you can use it for your application. So thank you very much for watching this presentation. I hope it was helpful for you. I hope you learned some data augmentation techniques that you can turn around and apply to your own object detection models to help improve their robustness or accuracy. I'll see you soon in the Q&A session. Thanks for watching.